Okay, so let's get started. We're at the hour. So good afternoon, everyone, and welcome to this joint ACOM EOL seminar. Frank, as I said, welcome everyone. Welcome to this. Welcome to this joint EOL ACOM seminar. It is my great pleasure to welcome Dr. Emily Fischer, who is a professor in the Department of Atmospheric Science at Colorado State University. She is also an affiliate faculty member of the CSU School of Global Environmental Sustainability. Dr. Fischer received her PhD in atmospheric science from the University of Washington. She completed a postdoctoral fellowship at Harvard University and then joined the faculty at CSU doing research in the realm of atmospheric chemistry and air quality. In addition to her atmospheric chemistry work, Dr. Fischer leads research to identify and test strategies to build more equitable and welcoming educational environments. This includes leading a mentoring program for undergraduates who identify as women and piloting best practices for preventing sexual harassment in field settings. She is also a founding member of Science Moms, a group of nonpartisan scientists working to demystify climate science and climate solutions. Dr. Fischer is the recipient of the AGU James B. McIlwain Medal. At CSU, her work has been recognized through the Montfort Professorship, an ABLE Outstanding Early Career Faculty Award, and an ABLE Outstanding Faculty Teaching and Mentoring Award. Emily's research focuses on using in situ atmospheric observations, satellite measurements, and chemical transport models to study emissions, composition, and impacts of non-traditional air pollution sources, including wildfires. And wildfires is a topic of her talk today. Dr. Fischer was one of the PIs for the NSF-funded We Can Field campaign in the summer of 2018 to study the composition of wildfire smoke. The NCAR C-130 aircraft, operated by EOL's Research Aviation Facility, was deployed, and Emily will talk more about aircraft observations from WeCan. So for those participating virtually, please be welcomed. You can ask your questions at the Slido screen at the bottom of the presentation, and we're going to save those for the Q&A session after the speaker's talk. Dr. Emily Fischer, welcome to NCAR, and the stage is yours.
Thank you. In case I move around. Thank you so much for having me. It's nice to see all of you. For those atmospheric chemists in the room, this is definitely not a chemistry talk. But those of you who are here probably already know all the chemistry that occurred during weekend anyway. So, all right, let's get going. I like to start with this photo. So this photo is the start of the Cameron Peak Fire. Those of you who are local, there's some people online, people in the room, right? My family was backpacking during the Cameron Peak Fire, and we, at about lunchtime, I had two whiny kids, and we stopped for lunch, and we sat down, and when we stood up after lunch and we looked back, we could see the plume kind of rising behind Cameron Peak. So that kid, who's now 9, ran the 6 miles out and we were fine. But that experience in summer 2020, in addition to WeCan, has really taught me a lot about fires and in many ways committed me to working on that. So we were there when it started August 13th, right? The Cameron Peak Fire became the largest wildfire in Colorado's recorded history. And it burned all the way almost to Fort Collins. So my heart goes out to all of you that have personally experienced this issue. I'm sure many people here and in the room have experienced it personally. These are just my photos from that summer, right, of the ash falling and all the light changes. And, you know, that's my birthday run in October when it was still burning. So on Earth, something is always burning. And so let me just see if I can start this video. I lost my mouse. Just go over. On Earth, somewhere, something is always burning. What you're looking at on the left, right, is the active fires. Those are gridded, right? And on the right is carbon monoxide. So anywhere where there's active burning, the atmosphere feels the effects. And an easy way to see that is a product of incomplete combustion, which is carbon monoxide. There are distinct seasons. So as we go through here, you'll go through the winter and it's going quickly, but you can see that we have different seasons for different parts of the globe. And the main thing to know that while we experience fires very viscerally here, most of the burning is actually occurring in the tropics. And North America is one place where the number and size of wildfires is going up, but that's not the case for the whole planet. All right, let's see if I can switch slides. Oop, can you go forward? Thank you. So almost all vegetated regions have free burning fires. And this is average. This is from a nice report from UNEP that they put together about 2 years ago about the rising threat of these sort of large, extraordinary landscape fires. But this shows the annual average fire density for a 20-year period. And you can see what I just showed you here. While we're, and I will continue today to be obsessed with fires in North America because that's where we live, most number of fires is occurring in the tropics. So wildfires are influenced by a lot of different factors. And I think during WECAN, this is one of the big sort of personal lessons about that I learned beyond atmospheric chemistry and atmospheric science. So fire behavior, I really do need to move. Can I just do that? It's very hard to stand at the podium. Okay, so fire behavior, right, is one fire intensity, spotting, fire spread rate, flame height, duration, is heavily influenced by both the topography. So during the Cameron Peak fire, part of why I was okay was where I was relative to the fire and it didn't jump over that ridge. Fuel. Moisture condition, vegetation types, content, continuity, amount, structure, right? We knew that that Cameron Peak fire was not going to make it to Fort Collins because there was a massive fuel break called Horsetooth Reservoir that it was probably not going to go over, and then it switches to grassland. Ignition sources, right? Cameron Peak fire was human started. We don't know how, right? But I was sleeping out that night. I know it wasn't lightning started. And so there's human activities, lightning, and then there's also these escaped fires, right, from human activities. During WECAN, right, we learned a lot about how fire management might impact fire behavior. So pre-suppression and current suppression activities, humans are always messing with and trying to move and control fire. And then weather, right, wind speed, direction, air temperature, relative humidity, stability, solar radiation, prior rainfall, all impact how fires are going to move. So for the rest of the hour, I'm going to focus just on North American fires, the smoke, and a bit about how I'm thinking about human impacts now. In general, this is where we're going. Fire activity is increasing, partially influenced by climate change. Smoke impacts people across the US, more to come for that looking forward. And on the human impacts, we need to build routine for checking air quality and protect the vulnerable people. So we'll talk about who's probably most vulnerable now in our communities. So wildfires in the Western US have become larger, hotter, and more destructive and deadly. That's known. You can get this from NIFC, and I just pulled it just to try to get the most current data, but you see this data in papers. That's annual wildfire acres over time. And you can see that we're just not in the same regime in terms of the size of fires as we were, of total burn area, as we were in the 1980s and 90s. We're just boop, step up. And there's a ton of interannual variability, which we feel here, right? 2020 was awful, pandemic, and also all those fires that were local. 2019 was okay. Last summer was okay. What's caused this? So there's a couple things. Land use practices in fire elimination over the last decades, mean that there's a lot of vegetation fuel buildup in fire-adapted western forests. So humans have been part of the problem. Livestock grazing is another issue. It's promoted highly flammable grass dominance in rangelands. there's a lot of recent development, right? So it's greatly expanded the wildland-urban interface, and that has increased human-caused ignitions. That's another factor. And then climate change has contributed to very large and very severe fires through a number of different avenues. So all of these things are a piece of why that plot looks the way it does, and that burn area has changed substantially over the last 20 years. So where are the wildfires? This is an interesting data set. This is getting old now, but I like to still use this. This is the Fire Program Analysis Wildfire Occurrence Data, so FPA-FOD, and it catalogs 2 million wildfires between a range of time. And what's neat about this data set is that it contains discover date, location, final size, and source of ignition. And source of ignition is sad and also funny to look at. It'll be like kid, drum, like whatever. It tells you what actually occurred and kind of puts blame on what happened with the wildfire. So anyway, one big picture here, now that we kind of zoom into North America that I want you to see, is that there's the Western US, this box, and there's the Southeast. Both are areas with a lot of wildfire activity. The West is very different from the Southeast, and for a couple of very important reasons. So one is the cause of the fire. So in the West, you have a substantial number of lightning ignitions. So the color here, the greenish is lightning, the orange is human, and the gray is unknown, so under some kind of under investigation, potentially human. So in the West, you have a lot of lightning ignitions, but you have a lot of human ignitions around where people live. And you can see the Front Range here. You could follow roads, and you can see the human ignitions increase. Also very different west to east is that in the Southeast, those fires tend to last pretty short. So they last 0 to 12 hours, less than 24 hours, right? The wildfires out here, many of them are lasting weeks to months. So it's a very different game. In the West, and I sort of point this out because these are the fires that we can targeted, and that's where I'm going, the largest wildfires, so things greater than 1,000 acres, maybe even greater than 10,000 acres, account for most of the US, the burn area in the Western US. So about 2/3 of them are lightning started, 1/3 are human started, and the big ones account for most of the area. And so this is from a smoke production standpoint, these are the kind of fires that we should understand what happens. All right, so climate change has many avenues to influence fires. So this is the start of the Cameron Peak fire, right, up there. And this is sort of a schematic of all the ways from again, this large UN report, right? So climate change is changing weather, changing rainfall anomalies, winds, the frequency of dry lightning, temperatures leading to longer wildfire seasons, and that is a change in our greenhouse gas emissions, and in my case, what I work on, our air pollution. So in North America, these are the things that we understand. Warming has enabled upslope advances in fires, so they're traveling further when they make runs up. About half of the increase in fuel aridity, or the dryness, since the 1970s is attributable to climate change at this point, and the estimates are that it's roughly doubled the cumulative fire area since 1984. It's the main cause for increasing fire weather, which in most cases is aridity or atmospheric thirstiness. So though sometimes I don't want to continue working on fires because I'm like, what are you doing? This is very stressful and very hard. I think we need to keep working in this space because it's this is what the future looks like. So increases in aridity, right? The one thing we know about the West is that temperature will go up, temperature goes up, vapor pressure deficit also goes up, dryness goes up. That when you have increases in aridity, that will increase fire where you don't have a fuel limitation. These extreme fire years, this is a probabilistic study, but it's one that really terrifies me. The extreme fires like we've experienced in 2020 may I don't want to say the word will because that stresses me out. I'm going to say may return on 3 to 5 year cycles. I don't really want a Cameron Peak fire every 3 to 5 years. That sounds awful. And we expect increased post-fire hydrologic risks with large rainfall events that fall on these burned areas. And so thinking about fires moving forward is going to be important from sort of all aspects of science and policymaking. All right, so let's talk about smoke. So after experiencing running from a wildfire, will never say that wildfire is not scary and that's not the human impact, right? This is awful, and I'm sorry for everyone that has lost homes and loved ones and things like this. But smoke is how most people in the US experience the impacts of fire. So if you think about these big fire plumes that hit DC, right, this past year, that hit the East Coast, smoke is how most people experience this hazard. So during the daytime, smoke in summer, not all in summer, throughout much of the year, throughout half the year, let's say, smoke is visible in satellite images. And so I show these because this is part of how we thought about planning for WECAN, is looking at these satellite images. And it's also, flying in WECAN changed my perspective of these images. I think you probably can't even see all the smoke that's in here, even though you see these like very clear areas here. You should think about the smoke as these little ribbons, some thick, some thin, all over the place, all over summer, across North America. It's kind of a component of atmospheric composition now, from May to October. And so this is a description of how you might have an operational data set of where smoke is. So these plumes that are shown here, this is from October 6, 2020, from when the Cameron Peak fire was burning, and also our other local fires at that time. And the gray here are smoke plumes, and these have all been hand-drawn by HMS analysts, like kind of I didn't demonstrate it on the last slide. And so there's lots of plumes. This is from one day. There's tons of plumes around. And they're present at many different altitudes, and they don't always reach the ground. And maybe you've experienced that here, right? Like in the afternoon, some of these big local fires, they shoot stuff up high, and in the night, maybe we had some local smoke impact. And you kind of see that here, right? California, in this case, is experiencing very poor air quality. All of these little triangles are EPA monitoring sites. The blue ones are the purple, not blue, green. The round ones are purple airs. And you can see that there's smoke overhead over the Midwest, right? But the air quality at the ground is good, right? So there's smoke there, but it's not impacting the people at the ground. If you look across North America, across CONUS, let's say, and you look across the whole fire season, and you take all those smoke plumes and you stack them up, you can get a sense of the % days of smoke overhead over North America. And it's there a lot. So this is an average of 2006 to 2020, and April, May, June, July to September, and that's the % days with smoke overhead. So every day, if there is one of those gray plumes that you can see from satellite overhead, give it a yes. And so for the Midwest, 50 to 60% of the time in a very average July or August, there is smoke overhead. And that's actually where smoke overhead tends to peak, in the Midwest, but it's not at the ground. And so it's dilute, and people might not even notice it, but it's changing the light that's reaching the surface, and it may or may not be changing the clouds. And so it's in an extreme year, in a 2020 by itself, kind of, if we were to plot just 2020 here, those numbers are 70 to 80% of the time. There's smoke overhead over the surface in a lot of the US in August and into September for that year, because it was a late start to the fire season. All right, so let's talk about WECAN. So WECAN was a real joy to lead. So people who are on WECAN, Frank, Becky, where's Sam? I lost him. There he is. Who else? Anybody else? Awesome. Okay, great. So this occurred in 2018. It was a collaboration between these 5 universities and NCAR. This is the PI team. And weekend was focused on wildfire smoke. So given that smoke is everywhere, weekend focused, it's important for air quality, nutrient cycles, climate, and weather. Weekend focused on 3 aspects of this. So one was the nitrogen in the plumes, what is emitted and how does that evolve? 2 was how do the aerosol optical properties change? And 3 was what happens when smoke and clouds mix together. So nitrogen is very important to the chemistry inside smoke plumes. It is one of the key drivers to how fast the chemistry changes in smoke plumes. And it's also critical to the nitrogen deposited to ecosystems. As a side note, I'm starting a new project where I'm going to try to use satellite observations to untangle how much nitrogen deposition is due to wildfires versus ag in the western US, because the frequency of smoke overhead is occurring so often and it contains a lot of nitrogen. In terms of the aerosol optical properties, like I just showed you, these rivers of smoke are present over North America a lot, and they change light availability, and part of being able to predict that is to be able to predict how the color of the aerosols and how they interact with light is changing. And then clouds chemically process smoke, and I'll show you some pictures of this. This is a little tiny one that we took, and there's smoke here and these little puffy cumulus clouds on top. So smoke particles can serve as cloud condensation nuclei, as in they can form cloud droplets. They can also serve as ice nuclei. So it's going both ways. The clouds are processing the smoke particles, and the smoke particles are impacting the formation of clouds. The third one was the hardest flight planning of all, to figure out how to get those samples. So during weekend, the C-130 was based in Boise. This occurred at the same time as BB Flux, which was a campaign with the Wyoming King Air, led by Rainer Volkamer at CU Boulder. And that's our joint team there. We based in Boise because from Boise, that circle, that red circle, is about 2 hours. So from Boise, you can access most of the, Eric, you are also there, sorry. I never went back over to this side of the room. This circle is about a 2-hour circle. So with a 5.5, 6 hour flight time, you could leave Boise, go somewhere, mess around, fly the wildfire smoke plume, and then do something on the way back, and spend about 2 hours there by an active fire. So I apologize. So when we put together the payload for weekend, I learned after the fact that that might have been one of the most complex payloads ever on the C-130, so thank you and sorry for the hassle. But fitting all of that stuff onto weekend, I think, is what's been responsible for the sheer number of papers that have come out of weekend, and the data set is still, I think, very rich, despite all the original graduate students that were on this project have moved on to their greener postdoc pastures. So this sort of data set is really beautiful still, and that combined with 2018 being a very active fire season, I think has partially made this really special. So there's Frank, Super Mentor Frank. I could not have done this without Frank. That's what the C-130 looked like from the back on this campaign. And I'll give you a picture of the front. There's 2 University of Washington graduate students, maybe one that you see here quite often because he's no longer a graduate student. Let's see, oh yeah, he's also a postdoc now. So what we did, these are our flight paths. We sampled smoke from more than 20 large fires. So these are the big fires. So Carr Fire, Mendocino Complex, these are big ones that you might have heard from, though there's been so many big fires since then. And what we would do is approach from behind a fire. So this is a good example shown here, and I'll show you this in a video so you can get a sense of what it was like. And then mow the lawn across the smoke plume. And that's what you see in all these pictures. And then the light blue that's here is where we were in smoke. So I want to show you And this, I was commenting in the beginning, this one would give Frank some PTSD, I don't know, hopefully not. This is what sampling the Kiowa fire was like. So that's, let me just move this over and see if I can get it to start at the right time. It's roughly there. Okay, so here we're flying the way home from some difficult cloud sampling, and we're crossing Idaho. And that's the back upwind of the Kiowa fire. So we would come around the fire. This fire was not actively fought, and it was sort of popped up and grew that day. When the pilots feel comfortable, then we turn into the smoke plume, which we'll do in a second here. And then, you know, Frank would say something like, it smells like barbecue. And then you go through the other side, and I say, oh, okay. And then we go back around. And then as the pilots get a little bit more comfortable, we'll circle back closer to the fire, but we need to stay out of the updraft. So, and you can't see, obviously, when you're in the smoke. So it's good to have visibility around the side. So we would do this, and so we'd just turn a little back towards the fire a little bit. Oh, we can get a little bit closer. That was fine. It wasn't very bumpy. And then come around. And so we would just do this. And this is going fast for those of you that are familiar with these cameras, right? It is, I don't know, 3 minutes in there of darkness. And I'm like, what am I doing? I have a 3-year-old, why am I doing this? So anyway, that's what we did. And then we would mow the lawn down the smoke plume. And sometimes we did a really great job of being pseudo-Lagrangian, where we were in time. We were always trying to be Lagrangian, but we weren't great at it. Some of these are, we're actually following the smoke, and sometimes we're just taking different samples of the smoke as it evolves and not going exactly with it, right? Because the fire's changing at the same time. All right, so that's how those flights worked. I just have to find my mouse. Okay, boop. All right, so this is what you get from that kind of aircraft sampling. You get here, this is the Taylor Creek fire, which we got very lucky. Actually, let's see, I have a few minutes. I tell you a quick story. We flew, this was the second flight, or RFO3, so new to doing this. We flew all the way out to Oregon, only to get there, that there was smoke everywhere. And we couldn't go down in it because we couldn't see anything and because there's mountains. And then we got very lucky. Thankfully, one little Taylor Creek fire was like, in a big complex, was like, I'll come out of the whole layer of smoke and give you something to sample. So we had this little plume that we knew exactly when it bubbled up, and we could follow it very closely. And this is the one where we did the best at pseudo-Lagrangian sampling. So this is us just weaving back and forth, trying to cross that smoke plume again and again and again. And we did 20 passes in this case. And this is what it looks like. So this is one of these segments. And you can see carbon monoxide goes up. I can't remember exactly at this point, but about 8 ppm, so 8,000 ppb is where your home carbon monoxide alarm would go off. So even in this dense stuff inside the cabin was fine, and outside the cabin was that. But it's very dense. And then ammonia, it's what my group, Alana Pollack, led those measurements. What we measured, and you can see it follows very closely to the carbon monoxide. So you use carbon monoxide because on the time scale of that we're sampling these plumes, it's a conserved tracer. So it has a lifetime of about a month. All these other things have much shorter lifetimes from down to seconds to minutes to hours. And so it allows us to control it allowed in weekend for us to control for dilution. So we know, oh, the carbon monoxide is chemically not changing. We can control for dilution and see how the chemistry is changing in the smoke plumes as they dilute downwind. And so, all right, so clouds. We pulled this off 5 times. We sampled smoke cloud mixtures. Here's an example of what that looks like. You've got like this blanket of smoke underneath and then popcorn clouds at the top. You can't really go in clouds right through them that are too big, right? That would be super bumpy. And so let me show you what that sampling was like so you get a sense. You have to find my mouse again. Tried to get these to start automatically, but that felt unreliable. So I put myself a note. All right, so let's go here. Oh, let's go take 2. Let's go here, 404-ish. Okay, so the first thing we do is go underneath, and then we would ask the pilots to come up into the clouds and go fly through the clouds. And we were trying, it was very unsuccessful and very hard, we were trying also to collect the cloud droplets in the cloud collectors that were on the wing of the plane. So this was, I get very sick actually on planes, and, but this was also just a very amazing experience. All right. So I just want to give you today just some of the very high level findings from WECAN, and I'll give you one or two in each of these topics. These are the kinds of things. There's been, I think almost 40 papers, something around 35 is what I was able to count last night, but I was like, oh yeah, I don't feel like that one's on the list. So, so in these three topics, here are some high level things that came out of WECAN. So this is all the nitrogen chemistry in smoke in a schematic. So I'll just walk through this really, really quickly. Half, when you burn something, about half of it is N2. Atmospheric chemists do not care about N2. Isn't that boring? And then half of it is what we would call the reactive nitrogen, or the fixed nitrogen. And in there, there's some reduced species, and then there's some oxidized species. So reduced species over here, oxidized species over here. One of the big things during WECAN that we were not even brave enough to write in the proposal, and I remember this being like, oh, should we write a thing about HONO? And we're like, no, if so-and-so's a reviewer, they'll think, no, you can't do that. And if so-and-so's a reviewer, so we thought it was too scientifically not certain to put it in the proposal. And so HONO, when this species is emitted, it's photolysed and it releases OH. And this paper from the University of Washington really helped us understand just how important HONO is for the OH budget in smoke plumes. And those of you who have any familiarity with atmospheric chemistry, this is the most important atmospheric oxidant. And so being able to measure all of these things during WECAN, right? This was measured, this was measured, this was measured, this was measured, 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 measured. We were able to say, okay, this is how much HONO there is. This is the fraction of nitrogen that's in that phase. This is how it varies, smoke plume to smoke plume. And this is its importance for chemistry downwind. And knowing that allows you to predict the OH downwind, which allows you to predict the lifetime of other things in the smoke plume. So this is a really critical piece that wasn't in the proposal because we were too scared because it was uncertain at that time, but I think it's a super important part of WECAN. So all that lawn mowing with the plane also produced a data set where we were able to quantify nearly all of the nitrogen in the plumes. And some of these bars are much more uncertain than other bars, but I still think it's the best data set we've ever had. So this is physical age on the bottom. So these are the freshest smoke plumes, right where I showed you in the video. And then you're going down to 5 or 6 hours. And so up top here is the number of passes that we did. So WECAN really focused on the near plume chemistry. So we have more data less than 2 hours old and less data as we get down to 6 hours old, right? Because we had to get there, fly around, let it evolve, and also get back to Boise. So we have fewer times where we were able to sample a smoke plume that we were sure that was the smoke plume and it was 6 hours old. And so we're able to see this evolution, right? We're able to see that, okay, here's the red is our HONO. The emissions, so the first thing to see here is that, okay, the emissions, there's chemistry happening very quickly. These are two primary emitted species, this one and this one and this one. Everything else is secondary. So even in the first hour, things are going to secondary species. And then over time, we're changing into a couple different bins. One is an organic nitrogen bin, one is a particulate nitrate bin, and one is a pan bin. And so how I'm using this next week is I'm going to the NADP meeting, and they've asked me to come to say, like, if we wanted to monitor smoke, what would we need to measure, right? And so from WECAN, I can say, okay, like, if you're getting anything greater than 6 hours old and you need to measure the oxidized size of things, some of these measurements are going to be a little bit hard, like this one, to do in a routine way. But this is roughly how much you would miss if you weren't doing that measurement, things like that. So also during weekend. So weekend was, I think the instrument teams had a great chance of success because we were allowed to do test flights 8 or 9 months earlier before the campaign. And so that allowed more junior teams with less experience to participate in weekend and do that successfully. And my team was one of them. And so at the time, there was no one who I could ask to measure ammonia. And I thought, I think this is going to be a really big part of the smoke plume for these nitrogen questions. So I'm going to burn the rest of my startup on this TILDIS, and Alana, as a spectroscopist, we're going to try. And so measuring ammonia in smoke was difficult. There were a lot of tricks to that. But I think because of WECAN, we're going to blow open the options for research on agricultural emissions. And so we can see that in Transium. So that's a King Air field program that I led that was a couple of years because we broke the plane 2 times. And then in 2023, this instrument flew as part of Aroma. And I'm currently working on another agricultural related opportunity where this instrument would shine. So particulate matter is the part of smoke that people see. And so WECAN, and you can ask Brett when you see him about this paper, but WECAN allowed us, because of the flight planning and the amount of things that were measured, helped us understand the ways that the particulate matter mass and how it absorbs light are evolving. So he was able to start splitting apart how much of what's emitted primarily is evaporating, and then how much of the gases that are emitted primarily are then being oxidized and contributing to the particle mass. And so that was possible. That was possible during WECAN. This is a picture of the smoke-filled boundary layer with clouds on top. And so this is a piece of the WECAN data set that I think is really underutilized, but really has potential still. From these types of flights, we're able to understand that smoke particles are acting as nuclei on which cloud droplets form. And those smoke-impacted clouds have 5 times as many droplets as a regular cloud, as a non-smoke-impacted cloud. And as a result, those droplets, given that you have to split up the water, right, are about half the size of clouds that are not influenced by smoke. So they're smaller, and there's more of them, which means the way they interact with light is different. And my hypothesis, not true, but I feel like this is a science project I would really like to contribute to if anybody wants to do it with me, maybe change the propensity for rain. So I think that's just given that they're smaller and there's more of them. Okay, so what else? So Frank and I feel like, did a really good job in the cockpit of finishing a thing and then being like, how do we still stay in smoke? Using the LiDAR from the University of Wyoming. And so every time we would be done with the part where we were in the fresh smoke plume, we would say, okay, is there smoke above us, below us? And the pilots were really lovely and being like, I'm like, can you go up 1,000 feet? Could you go up 500 feet? How much could you go up or down to like make sure we were in the smoke? And so that made essentially a library of mixed stage smoke that then, because of the beautiful VOC data sets, we were able to age. And so we have now a library of not in smoke, young smoke, medium age smoke, older smoke, and oldest smoke. We also have the in and out of Boise. So a small western US city constantly being sampled for 36 times, let's say, in and out. Sometimes there's smoke like this, and sometimes there's not smoke like that. And that data set, we're sort of able to extrapolate to, in a better way than routine monitoring is able to, what happens when smoke comes to town, in addition to just fine particulate matter goes up. So these are pictures from DC, right? So this is DC 2023. DC a few weeks earlier with no smoke. The AQI, just based on particulate matter, is the color there, right? So it goes from smoky and gross to clean up top. So from Boise, we know that these are the percent increases in the mean concentration of things during wildfire smoke events. So yes, carbon monoxide goes up, right? That's incomplete combustion. In smoke, carbon monoxide goes up. Also, ozone goes up. Those are two criteria air pollutants that increase when smoke is there relative to periods without smoke. Same thing in the Front Range. When we have smoke that comes to town, you get an ozone boost here, no matter what other junk we're also making on our own. These are all hazardous air pollutants. So acetaldehyde, formaldehyde, benzene, acrolein, heptane, and there's a larger list. The hazardous air pollutants all go up, and the percent increases of those are also quite high. And so part of what my team's been doing now is thinking, okay, can we, based on smoke age, ratio those to the fine particulate matter that's measured at the ground to get a sense of what people are exposed to from a hazardous air pollutant side of things, not just a criteria air pollutant side of things. So it's useful for that. So overall, we can taught us just how fast smoke chemistry is happening, and that the near-fire chemistry really matters for the partitioning of specifically nitrogen-containing compounds, which really matters for ozone chemistry in wildfire plumes. Smoke impacts clouds. The cloud particles are smaller. Smoke elevates criteria air pollutants and hazardous air pollutants. So a small city becomes a large city in terms of its hazardous air pollutant concentrations when smoke comes to town. It's something like, it's about that. When a sort of mixed concentration, concentration smoke plume comes, Boise is like New York in terms of its hazardous air pollutant concentrations. That impact is national because many of these things have lifetimes that they're certainly still present in the smoke plume when it comes. And it necessitated analytical development that was rapidly leveraged, now we can see, over the 5 years following, which is, I think, pretty exciting. So let's move on to those impacts. So this is from the last year's National Climate Assessment. And so this is, I think, a nice figure that I think demonstrates just how important interdisciplinary work on this is, right? So the fire suppression and past land use is facilitating conditions that are prone to stress. We see large and severe fires that they're altering vegetation and habitat, debris flow, reduced access. What's risks to infrastructure, risks to property? I'm going to focus on the two places that are people related. So smoke is a notable health risk for sensitive individuals. And I just wanted to, if this will play, this is what we have put together for Science Moms. Oh, you're lucky it's not playing. It's hard to watch. Okay, so I'll see if I can get that to play after, but that's a kid wheezing, and it's very visceral. And so populations, when they're exposed to smoke, experience, and she's searching for her inhaler, and she's wheezing. Exacerbations of asthma, asthma hospitalizations, ED visits, OFFIT visits, outpatient visits, inhaler medication refills. All of these things are happening when it's smoky outside. It's exacerbating COPD, creating higher risks of respiratory infections, all the way down to cardiac arrest and mortality. So who are those people that we really need to care about? Kids, the elderly, others with pre-existing conditions. In addition, outdoor workers, people who can't make the choice to go inside. So another thing that I'm working on with a team at CSU, and this is very hard work that I have a love-hate relationship with because I feel it's very important. I also feel like I'm not the right leader. I also feel like we have to keep going, is we're working on creating decision charts that are customized to sensitive groups that may need more support in making their decisions in smoke-impacted periods. So this is an example chart that we piloted last summer with outdoor workers in the city of Fort Collins to give example of activities by intensity and what they could do under different conditions. And we're trying to help them disentangle what to do in ozone versus fine particulate matter in summertime for outdoor work in the Front Range. We're working right now on figuring out how to co-create something like this for manufactured home communities in Boulder. And that's this whole new challenge of working for me in multiple languages. So we can also build a huge amount of capacity. I'm an example of that capacity. But let me go through this. So NOAA, NASA Fire XAQ, that occurred the summer after. Our flight patterns and safety protocols with the US Forest Service were really, I think, important for that campaign. Right now, there's a development of aerosol parameterizations within cloud and mesoscale models that should be helping National Weather Service weather forecasts in smoke-impacted locations. This is what's continuing now with the WECAN data set that I can see, adjustment of chemical transport models to try to include missing chemical processes that are clearly important from the WECAN data. WECAN also, I'm really proud of the team for piloting best practices in preventing sexual harassment. WECAN happened right after that National Academy report came out on sexual harassment in field programs, and the WECAN team was very gracious in allowing us to try to figure out what the best practices would be for training a team and surveying pre and post and people sharing their experiences. I'm super grateful to the public education. That was the videos and lesson plans are super fun. I'm not showing them here today, but when I normally give a public talk, I show those videos that your team made as part of that talk. We have better impact assessments, right? Because we know better what's in smoke, and so we can identify potential health effects. And this is an example of just sort of the growth, right? I could point to many grants and many projects that for me, because I understand smoke better, I've been able to contribute to. The NSF EPSCoR in Montana, Lou Hu is a key person on that, right? And WECAN was really the first big mission of his career. So his sort of faculty position. So that's just awesome. So thank you. I'm happy to talk about any of this. There's a lot of papers. If you are a chemist and you're looking for some low-hanging fruit, I never finished the ozone paper. We could do that. There's still, I think, a bunch on aerosol cloud interactions that's underutilized in the data set. I have a student working on actinic flux impacts, and we'll run out of time, and she'll graduate. And I think there's a lot more that will be able to be done there that we won't be able to figure out. So if Sam would allow you to work with him, that's another area I think we could really connect things still. So that's that. I'd love to take questions.
Thanks, Emily. We have plenty of time for questions, and the audience are online. All this brain power in the room, and no one has a question.
Oh, something, but I have to read it.
Someone has a question. Lady Mateus asks, I would like to know how to use the black carbon concentrations as a tool to evaluate the impact of fires and air quality in urban areas, taking in consideration that the black carbon that generate traffic is larger than fires in this kind of environment.
Sure, so maybe I'll just take a step back and talk about how you might use, how you can discern, how you can have your best estimate of whether smoke is impacting an urban area. So, and I'm laughing a little bit because we're doing this with the aroma data right now at my group, trying to make sure we take out every last bit of smoke, which for Chicago is very hard. So, you should use other information in addition to the local chemistry on the ground to support your hypothesis that smoke is impacting the air quality there. So the first one would be to use satellite data. So we have, over the US, we have a really good idea of whether there's likely smoke in an urban area because you have the HMS smoke plumes to use. And they're, you know, especially very recently, right, they're put out many times throughout the day. So you could first check that and say, okay, is there wildfire smoke over an area? Then you don't know if it's at the ground, but you know if it's likely present in the area. So that's step one. Step two would be to look not just at black carbon on the ground, but to look at any fine particulate matter measurements. So the regulatory monitors, and if they're not available because they're sparse in many areas where wildfire smoke is present, use the purple airs. So the purple airs just require a little bit of thought. You gotta make, they're not to put down purple air, but they die in about 2 years. I've had one at my house, right? You got to make sure the two channels match. You have to do a little bit of care with the purple air network, but it's a beautiful data set if you do that care. Then you can figure out, okay, is that amount of particulate matter greater than like 1 standard deviation above the norm for that city? So smoke overhead and the PM at the surface is elevated. Okay, now we can look at other impacts on air quality in that area. So it's a bit tricky to use black carbon, and actually most of the aerosol in smoke, I didn't have this here, but I could show you, the AMS data from WECAN show black carbon is only a small part of smoke. Most of it is organic carbon. Actually, a very small amount is black carbon. And so the composition of an urban area and wildfire smoke are quite distinct in terms of their total particulate composition. Whether you have that information for the urban area is another question or not, but they are chemically distinct. So anyway, I hope I got to that question. Maybe I'll take the next one. With escalating fire frequency and severity of wildfires in the US on potential for utilizing untapped data from the Weekend campaign to further enrich our understanding of atmospheric chemistry. So I'm gonna answer this a little bit differently. I'm trying to figure out how to work on prescribed fires. So I'm gonna gently take off. It's still nearby my atmospheric chemistry hat, but put on an atmospheric science hat and think about how I can work with fire scientists to figure out how to enable more prescribed burning. Because I actually think that is what needs to happen. Not that we don't need to know more about smoke chemistry, but I feel like I'm at a limit of what I can do to contribute to that. But I know a lot about fires now, and my next projects, I am aiming them toward increasing and supporting prescribed burning. So I think figuring out how we can light fires safely and have the smoke not hit people and prevent health impacts, I think, is one of the most important things I could do. Yeah?
We have some questions in the audience.
Thank you, and a great talk. I was curious what you learned about the evolution of black carbon and the hygroscopicity of black carbon, and then also the evolution of organic carbon particles.
You should ask Brett about the evolution of organic particles. The black carbon should be becoming more hygroscopic. Everything's becoming more hygroscopic as with time. We didn't do anything specific with black carbon and hygroscopicity, though. But everything is going in that direction.
We have a question online by Bill Hayes.
Wait, I think there was like a
we're going
hand.
To go back and forth.
Okay, sorry. You're in charge. Okay, I was like, there was a hand wave of something over here.
I saw that. I saw that.
All right, so
Oh,
Bill. Hello, Bill.
The question is, do you have an idea of how much of the ozone produced in the smoke plumes becomes ground level ozone? Decision charts such as these are very valuable tools for those of us who work in the public health. Thank you.
I think to answer that question, Bill, what we could get is a probability distribution of how much at a given temperature. So ozone in the front, just let me take a step back. In most places, ozone and temperature are some kind of linear relationship. It's not perfect, it's like a shotgun blast linear relationship, but generally hotter days have more ozone. So at a given temperature, smoke versus a period with smoke and no smoke, I think we could know a range of extra ozone anticipated for many monitoring sites with long-term data now, because we have had, over the last 5 years, many past examples of smoke of various ages, of various concentrations coming to the Front Range. And so that number, if it's really, really dark and really fresh, that number might be very small or negative. But if it is aged, I would guess that number ranges from 3 to 10 ppb. And so we'd have to go look at that, and we could redo an analysis by Steve Bry a long time ago that ended with data in 2015, where in that case the Front Range wasn't yet significant in terms of its changes to ozone because there weren't as many smoke-impacted events. But I think we could know that, Bill. And I have a thought about how to do it. So we could make something like that. I think if that would be useful. Maybe we can make that for the EPA project. Maybe that could be a job we could do. Okay.
I think we have a question.
Yeah.
Hi, thank you so much for talking to us about this. I actually had a question about prescribed burning.
Yeah.
Glad that's your interest. What do you think is like the feasibility of doing kind of prescribed burning in this area, considering Denver's problem with ozone non-attainment?
Yeah, it's hard. It's really, really hard. But what scares me most is that climate change will close all the prescribed burning windows. And the prescribed fires will get out of control and like those kinds of things. So I actually think it is very hard here, and we really have to work on it, because this is a wildfire is a crisis, and prescribed burning is one way out of the crisis. And so, yes, it's much easier to let things burn away from population centers. But there is a very narrow window too, as I understand it, between being able to light a fire here, when there's this window from snow on the ground to like, now the spring is super windy here, to now it's dry, and now at the risk of wildfire. It's a very narrow window. So I would really like to use some of the ways we've thought about climate controls on wildfires to think about if we can open up prescribed fire opportunities. And I think there's also a bit of a tension there, right? Because as atmospheric chemists, we've been like, look at the smoke, super bad, don't breathe it, right? Which is yes, and thoughtful smoke at a low intensity in off times of year when it's most likely not hitting large population centers is going to be a really important thing. And so I think there's also a communication. I would love to figure out how to enable the communication scientists to help us with that transition too. Sorry, it's not a great answer, but yes, it's really hard. It's much easier to burn in other places.
We have a number of questions online.
Yeah.
The first one is by Maria Paula, and she says, thank you for a really nice talk. What do you believe is the most important current challenge for investigating the ozone generated from fire emissions?
Well, the easy thing I could do is finish the paper from weekend. There was a really, thanks, everybody on weekends like, don't you have half a paper? I was like, yeah, I kind of do. But then the pandemic happened, and then I have students who need to finish, and then it's a backseat. I also never wrote the weekend overview paper because of the pandemic. So I think this is still an observationally supported question, and most of our models are not going to do a good job at it. That's my first thought about this, based on our experience during WECAN. And I think some of the analysis techniques from FireX applied to the WECAN data would be a very good science step for ozone chemistry. Because the WECAN data, not because of anything I did, more active fire season, right? Much more data than the FireX data for this kind of question really near to a fire.
Brett, did you want to ask a question, or did you want to ask the question online?
Or you want?
I wanted to invite Emily to address the question about public access of your data set before I trumped that one.
Lovely talk. Where is the public?
Just the second.
Now it's top. Whether you, oh, WECAN data is publicly accessible. And we were not able to distinguish much by fuel type. So when a fire burns in real life versus a lab, you should actually think about it as many fires. A big fire is actually many fires. And the smoke that we were sampling was being sucked up from like an area of smoldering and an area of flaming, and then there's some grasses, and then there's some trees, and then there's some shrubs, all being pulled into a same plume. So we do see similar emission factors for nitrogen-containing compounds for lab studies where we looked for WECAN, but it's loose. So WECAN is not a good data set, and we only really had one big grass fire. So not really, there's not much for that data. With escalating, sorry, I'm interested.
I have a question.
Yes, okay, sorry.
It's a little bit selfish.
Do it.
So you had that nice decision chart for public workers outside. But I'm interested in whether you think, schools and soccer leagues and little leagues in the Front Range have appropriate guidelines for when, or kids going out to recess.
I don't think so, and I think that would be another great target population as the wildfire smoke season particularly attacks the front of the school year, right? Compared to the East Coast, my kids start school so early here, it's like mid-August. So they have a month and a half of prime fire season. So yes, I think we need to do that. That being said, I soccer mom so hard, and the Arsenal in Fort Collins, there was a smoke thing about a year ago, and I was very impressed with Arsenal's message, like compared to the school. So I think sporadically there are people who know-ish what to do, but it's very haphazard. So not to put down like all of Fort Collins doesn't know how to make decisions. I was like, oh, Arsenal soccer, whoever's in charge is like getting it down. I was like, this is a fine recommendation. I would say the same thing, orange or above, call practice, just be done for today. That's where I notice the kids feeling it, slowing down, and if the kids are feeling it, I would slow things down. But yes, that would be great. Another group while we're on this topic, where I think we should work is with the elderly specifically. So that's another group that I feel like my project might not get there.
So we have 2 comments online,
Yeah.
so I'm just going to read them one after the other if you want to respond to them. And one of them is by Masiat Hossein. I apologize if I botched your name up. But he says, with the escalating frequency and severity of wildfires in the U.S., I'm interested in your perspective on the potential for utilizing untapped data from the Weekend campaign, as you mentioned, to further enrich our understanding of atmospheric chemistry.
So one thing that you could do with the Weekend data that I think would be smart, that's not exactly atmospheric chemistry, but I think would be important. So wildfire plumes have hit big East Coast cities. So you have a huge N population now. And we actually know relative to fine particulate matter concentrations roughly what was in that air. So I think there should be a bunch of health studies on the East Coast populations that experience the smoke plumes. I think that should be very rich because the N is so large, right? So you might be able to detect health outcomes that are less likely and understand what was happening. So I think that would be useful. That would be a useful thing to do. I think that more could be done with smoke and clouds. We jammed that bit into the very end, the analysis, not the sampling. I also think it would be good to, and I'm not sure if this is going to happen, maybe it'll happen. When we were sampling during weekend, we had a very hard time getting into fully liquid clouds. We would show up and there would be ice clouds. And that was annoying for everybody because none of the inlets were set up to sample ice clouds. So I think sampling smoke impacted ice clouds would be another thing that I would do. I'm not the right person to do that, science, but that's something I would do because many times we would get there and be like, shoot, not water. We should be asking questions about ice. Why are we not doing that? We can't do it. Okay, go back, do something else.
And then the other question is by Betsy, or it's more of a comment. Lovely talk. Most aircraft campaigns look at near-fire young smoke, less than 12 hours, in identifiable plumes. Long-range transport also happens greater than days. Example, West Coast to Colorado or further east. Thoughts about studying that?
Yeah, so when California burns, that is the equivalent of, it looks something between orange and purple sampled in Weekend chemically. So the Weekend data set has that. And the other thing I would say is that there have been many airborne campaigns, particularly many large NASA campaigns, right? And they are always out doing something else. Aroma, great example. Trying to study urban air quality, trying to study something else, smoke shows up. And so there's many, many data sets that have old smoke in them that could be mined in various different ways. And people did that ahead of these other field campaigns to kind of know what to sample in. But actually the old smoke, there's lots of good campaigns of that, even at the ground. So like I worked when I first moved here at Erie in 2014 and 2015, and we were trying to figure out the impact of oil and gas on ozone. That was what the campaign was. But the first paper we wrote was about smoke because it came for 3 weeks. And so we had this nice chemistry data set, but it was smoke impacted even though it wasn't supposed to be.
So I'm going to ask one more question online, and then Frank will have the last question in the audience. The question is by Lindsay Anderson. Thank you for your talk. Was there data from Weekend measuring plume heights of the smoke through something like a dial instrument, or was that not part of the payload?
Nope, we only used the LiDAR for navigation purposes, and that data, we were trying to use it for something. That's hard data to use science-wise. It hasn't been processed and thought through as much as it should be, so no.
Just a comment. We should really finish that ozone paper. And,
I know.
I've been dabbling.
You and Dan Jaffe.
Yeah, I always dabble in that, and then I forget, and then I do something else.
Yes.
But if you do plot the high PM events in the Front Range, ozone flattens out.
Yeah,
and
super high.
I think what's happening is that the ozone that you would have otherwise made, if there wasn't any smoke, goes down.
Yeah.
And what you add in with the smoke fills up the rest, and so it doesn't do anything, right? I think that's really cool, and I think we should look into trying to.
I think we should too, and maybe, so Kimberly is working with Sam, maybe going to meet this afternoon, and Kirk is getting a good handle, I feel, from the Central Valley flight This.
I was going to mention agricultural workers too.
Yes, agricultural workers, yes, different than outdoor workers in some ways than the ones we're working with. But yes, agricultural workers are very vulnerable, also vulnerable to dust. So this flight of old, well-mixed smoke, what's the change in that down actinic flux? Like, what is the change at the ground? And we should know that. And TUV is doing a pretty good job, order of magnitude, predicting it, which I feel like maybe then we can learn something about the smoke chemistry here from. I am sorry, we can co-authors, for having a paper sitting in my Dropbox folder.
And with that, we are past the seminar hour. Emily can stay with us for another hour, so I've invited her to have lunch with us at the cafeteria. So if you're interested in talking with her some more on some of the research that she's doing, or ask her some questions, or start a collaboration, please come and see her in the cafeteria. Let's thank our speaker one more time. Thank you.
Or you can just email me, or come to Fort Collins. I'm not hard to find.